Tonight, we're exploring one of the most profound and unsettling truths about our universe. The cosmos is expanding, and it's expanding so fast that civilizations on opposite sides of the observable universe could never meet, no matter how advanced they become. Somewhere out there, maybe in a galaxy a billion light-years away, there might be a civilization. They might be ancient, millions of years old, far more advanced than us. They might have mastered space travel, built starships that can cross their galaxy in years or decades. They might have looked up at their night sky, seen our galaxy as a faint smudge of light, and wondered if anyone lives here. And it wouldn't matter. They would never arrive. Because the space between us is growing faster than they can cross it. By the end of tonight, you're going to grasp how space itself stretches between galaxies. Understand the role dark energy plays in pushing galaxies apart. And discover that while distant civilizations can never reach us, our local cosmic neighborhood still contains trillions of stars where life might exist much closer to home. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something most people think they understand, but actually don't. The universe is expanding. You've probably heard this before. Scientists discovered it in the 1920s. Edwin Hubble showed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This discovery revolutionized our understanding of the cosmos and gave us the Big Bang theory. But here's what most people miss. When we say the universe is expanding, we don't mean galaxies are moving through space like boats spreading out across an ocean. We mean space itself is expanding. New space is being created between galaxies constantly, every second, everywhere. This isn't a subtle distinction. It's the difference between galaxies moving away from each other and the very fabric of reality, stretching, pulling everything apart. Think of it like this. Imagine you have a balloon with dots drawn on its surface. The dots represent galaxies. As you inflate the balloon, the dots move farther apart, not because they're sliding across the rubber, but because the rubber itself is stretching between them. That's what's happening in the universe. The space between galaxies is literally growing, being created out of nothing, expanding the distances between everything. This has been happening since the Big Bang, roughly 13.8 billion years ago. Back then, everything in the observable universe was compressed into an incredibly hot, dense point smaller than an atom. Then, expansion began. Space itself started growing, cooling as it grew, and eventually forming the stars, galaxies, and structures we see today. And this expansion never stopped. It's still happening right now. Every second, the universe gets bigger. New space appears between distant galaxies, pushing them farther apart. Now, here's where it gets interesting. The expansion isn't the same everywhere. Gravity can overcome it locally. Our Milky Way galaxy isn't expanding. The stars within it stay bound together by gravity, orbiting the galactic center in organized patterns. The solar system isn't expanding either. Earth remains at a stable distance from the Sun, held in orbit by gravity. Even our local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, isn't expanding. These galaxies are gravitationally bound to each other. In fact, Andromeda is actually moving toward us, and in about 4 billion years, it will collide with the Milky Way. But beyond our local group, expansion dominates. Distant galaxy clusters are all moving away from us, carried by the expansion of space. And the farther away they are, the faster they're receding. This relationship was discovered by Hubble and is now called Hubble's law. It states that the recession velocity of a galaxy is proportional to its distance. Double the distance, double the recession velocity. Triple the distance, triple the velocity. The constant of proportionality is called the Hubble constant, and measuring its precise value has been one of astronomy's great ongoing projects. Current measurements put it at roughly 70 kilometers per second per megaparsec, or about 43 miles per second per megaparsec. Let me break that down. A megaparsec is about 3.26 million light years. So for every 3.26 million light years of distance, a galaxy's recession velocity increases by about 70 kilometers per second, or about 43 miles per second. A galaxy 1 megaparsec away is receding at about 70 kilometers per second, or about 43 miles per second. A galaxy 10 megaparsecs away is receding at about 700 kilometers per second, or about 435 miles per second, and so on. This might not sound dramatic at first. 70 kilometers per second is fast, but it's still less than the speed of light, which is about 300,000 kilometers per second, or about 186,000 miles per second. But here's the problem. This relationship continues indefinitely. Keep going to more distant galaxies, and eventually you reach a distance where the recession velocity equals the speed of light. And beyond that distance, galaxies are receding faster than light. Wait, you might be thinking. Nothing can move faster than light. Einstein proved that. And you'd be right. Nothing can move through space faster than light. But space itself can expand faster than light. There's no cosmic speed limit on the expansion of space. Einstein's relativity limits how fast objects can move through space, but it says nothing about how fast space itself can grow. So there exists a distance called the Hubble radius, or the Hubble sphere, beyond which galaxies are receding faster than the speed of light due to cosmic expansion. This distance is about 14 billion light years. Galaxies beyond this boundary are moving away from us, faster than light can travel toward us. And this creates a profound problem for communication and travel. If a galaxy is receding faster than light, then light from that galaxy can never reach us in the future. Actually, that's not quite right, and the details here are subtle and important. We can see galaxies that are currently receding faster than light. How is that possible? Because the light we're seeing now was emitted when those galaxies were closer, when they weren't yet receding faster than light. That light has been traveling toward us for billions of years, fighting against the expansion of space, slowly making its way across the growing distance. Eventually, it reaches us, and we see the galaxy as it was billions of years ago. But here's the key point. If we tried to send a signal to that galaxy now, our signal would never arrive. The space between us and them is expanding faster than our signal can cross it. The signal would travel outward, moving at the speed of light, but the destination would be receding faster than that. The signal would never close the gap. It would keep traveling forever through expanding space, getting farther from us, but never reaching its target. This defines what's called the cosmic event horizon. It's the boundary beyond which we can no longer influence events or receive signals from them. For us, right now, the cosmic event horizon is at about 16 billion light-years. Galaxies beyond that distance are forever beyond our reach. We can see some of them, the ones whose ancient light is still reaching us, but we can never communicate with them or travel to them. They're on the other side of an invisible barrier created by cosmic expansion. And this barrier is growing. As the universe expands, more and more galaxies cross beyond our cosmic event horizon. Galaxies that are currently within reach will eventually recede beyond it. Given enough time, billions or trillions of years, every galaxy outside our local group will disappear beyond this horizon. The universe we can interact with is shrinking, even as the total universe grows. Now, let's talk about what this means for aliens. If intelligent civilizations exist elsewhere in the universe, and there's good reason to think they might, where are they? Could we ever meet them? Could they ever meet us? The answer depends entirely on where they are. If aliens exist in our galaxy, the Milky Way, then expansion doesn't matter. The galaxy is gravitationally bound. Expansion doesn't affect it. An alien civilization on the other side of the Milky Way could, in principle, travel here or send signals here. It would take a very long time, tens of thousands of years, even at near light speed, but it's physically possible. The same goes for civilizations in nearby galaxies. Andromeda, the Triangulum Galaxy, and the other members of our local group are all within reach. They're gravitationally bound to us, moving toward us or orbiting with us, not receding away. A sufficiently advanced civilization in Andromeda could send signals or even spacecraft to the Milky Way. It would take millions of years. Andromeda is about 2.5 million light-years away, but again, it's physically possible. But beyond our local group, everything changes. The Virgo cluster, a massive collection of galaxies about 50 million light-years away, is receding from us. Not quickly. Its recession velocity is only about 1,000 kilometers per second, or about 620 miles per second, but it's moving away. An alien civilization in the Virgo cluster could still send signals to us now, and those signals would reach us eventually. But they couldn't send signals forever. Eventually, as expansion continues, the Virgo cluster will recede beyond our cosmic event horizon. At that point, any signal they send will never arrive. The growing space between us will swallow it. For more distant galaxies, the situation is already hopeless. Consider a galaxy 1 billion light-years away. Its recession velocity is about 20,000 kilometers per second, or about 12,400 miles per second, roughly 7% of the speed of light. An alien civilization there could send us a signal now, and that signal would reach us in about 1.1 billion years, accounting for the expansion that occurs during the signal's travel time. But what if they wanted to visit us? What if they built a spacecraft capable of traveling at 99% of the speed of light, an almost inconceivable achievement requiring technology far beyond anything we can imagine? They point their ship toward the Milky Way and accelerate to near light speed. Would they ever arrive? No. The space between their galaxy and ours is expanding faster than they can cross it. They would travel outward at 99% of light speed, covering vast distances, but the Milky Way would be receding away from them. The net result is that they'd make no progress. The distance would stay constant or even grow. They could travel for billions of years and never get closer. They'd be running on a cosmic treadmill, expending enormous energy, covering enormous distances in their local space, but making no progress toward their destination, because their destination is receding as fast as they're approaching. Eventually, they'd run out of fuel or resources or time and have to give up. The journey is impossible, not because of technological limitations, but because of the fundamental nature of space itself. This is the barrier that cosmic expansion creates. Beyond a certain distance, travel becomes impossible regardless of technology. You could have unlimited energy, perfect engines, ships that travel at 99.999% of light speed, and it wouldn't matter. Space itself is expanding faster than you can cross it. The destination recedes as you approach. You can never arrive. Now, it gets worse. The expansion of the universe isn't constant. It's accelerating. This was discovered in 1998 by two teams of astronomers studying distant supernovae. They expected to find that expansion was slowing down over time, pulled back by gravity. Instead, they found the opposite. Expansion is speeding up. Galaxies are receding faster now than they were billions of years ago, and they're receding even faster still as time goes on. This acceleration is caused by something called dark energy, a mysterious component of the universe that makes up about 68% of its total energy. We don't know what dark energy is. We don't know why it exists. We don't even know if it's really an energy in the normal sense. What we do know is that it has a repulsive effect, pushing space to expand faster and faster. The nature of dark energy is one of the biggest unsolved mysteries in physics. Is it a property of space itself, something intrinsic to the vacuum? Is it a new field permeating the universe? Is it a sign that our understanding of gravity breaks down on cosmic scales? We don't know. What we do know is the effect it has. It's causing the expansion to accelerate, and this acceleration means that the cosmic event horizon is not fixed. It's moving. Galaxies that are currently within reach will eventually move beyond it. The sphere of space we can interact with is shrinking over time. Let me give you some numbers. Right now, the cosmic event horizon is at about 16 billion light-years. That's the farthest distance to which we could send a signal and have it eventually arrive. But as expansion accelerates, this horizon will start to shrink. In about 100 billion years, the horizon will be much closer, perhaps only a few billion light-years away. Galaxies beyond that distance will have receded so far and so fast that no signal from us could ever reach them. And this process continues. As we move further into the future, the horizon shrinks more and more. Eventually, in the far future, trillions of years from now, every galaxy outside our local group will have disappeared beyond the horizon. The local group, the Milky Way, Andromeda, Triangulum, and a few dozen dwarf galaxies will merge into a single giant elliptical galaxy. And that galaxy will be alone in an empty universe. From the perspective of observers in that future galaxy, the rest of the universe will be gone. They'll look out into space and see nothing. No distant galaxies, no cosmic microwave background, no evidence that a Big Bang ever happened. If they didn't have historical records from before the galaxies disappeared, they wouldn't even know the universe was bigger than their local galaxy. They'd think they lived in a static, eternal universe consisting of one galaxy surrounded by infinite, empty space. They'd be completely wrong, but they'd have no way to discover their error. The evidence would have literally moved beyond their reach. This raises a disturbing question. Could we be in a similar situation right now? Could there be parts of the universe that have already receded beyond our cosmic event horizon, parts we can never see, evidence of past events we can never detect because the light has been redshifted and stretched beyond recognition? The answer is yes. There are parts of the universe we can never see. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light-years. That's the farthest we can see in principle, even with perfect telescopes. But the total universe is larger than that, possibly infinitely larger. There are regions of space so far away that light from them hasn't had time to reach us yet. And, because of accelerating expansion, light from some of those regions will never reach us. They're beyond the cosmic event horizon and always will be. The universe is bigger than we can ever observe, and parts of it are forever beyond our knowledge. Now let's think about what this means for the search for extraterrestrial intelligence. We've been looking for alien signals for decades, listening with radio telescopes, searching for anything unusual or artificial in the electromagnetic radiation reaching Earth from space. We haven't found anything yet, but we've only searched a tiny fraction of the sky in a tiny fraction of possible frequencies. The search continues. But here's something most people don't realize. If aliens exist in a distant galaxy and they're sending signals toward us, we might see those signals, but we can never respond in a way they'll receive. If they're beyond our cosmic event horizon, any reply we send will never reach them. The distance between us is growing too fast. This means any communication with civilizations in those distant galaxies would be one way only. We could receive their messages, learn about their culture, their science, their history, but we could never send a response they'd actually receive. We'd be eavesdropping on a conversation we can never join. And it's even stranger than that. If a distant civilization sent a message to us 1 billion years ago, that message is traveling toward us right now, crossing the expanding space between galaxies. But if we tried to send a message to them now, our message might never arrive, even though their message to us will arrive eventually. The expansion during the billion years since they sent their message has pushed them farther away. They might now be beyond the distance where our signals can reach. Time matters. The earlier a civilization sends a signal, the better chance it has of reaching distant galaxies before expansion carries them beyond reach. Civilizations that arose early in the universe's history, perhaps 10 billion years ago, when expansion was slower, could have sent signals that reached much farther than signals sent today. Those ancient civilizations might have communicated across distances that are now impossible to cross. By arising late, we might have missed the window for communicating with much of the universe. Here's another disturbing implication. Imagine an alien civilization exists in a galaxy 2 billion light-years away. They're an ancient, advanced civilization, millions of years old, and they've been broadcasting signals for all that time. Those signals are traveling toward us right now. In about 2 billion years, accounting for expansion, the first of their signals will reach Earth. But by that time, Earth will be completely different. The Sun will have expanded into a red giant, likely destroying the inner planets, including Earth. If humanity, or any descendants of humanity, still exist, they'll be living elsewhere, perhaps on planets around other stars, or in artificial habitats, or in forms we can't even imagine. There's no guarantee anyone will be listening for signals. There's no guarantee anyone will even be there to receive them. The timing has to line up perfectly. a civilization has to exist, be listening, and be in the right location when the signal arrives. And for distant galaxies, that window is narrow. By the time their signals reach us, we might be gone. And if we send signals to them, those signals might arrive when they're gone. Two civilizations could exist, send messages to each other, and both messages could arrive to find nobody home. Ships passing in the night on a cosmic scale. Let's go deeper into the math of expansion. The Hubble constant, that's 70 kilometers per second per megaparsec, or about 43 miles per second per megaparsec, tells us how fast galaxies are receding based on their distance. But it's called a constant only in the sense that it's the same everywhere in space at any given time. It actually changes over time as the universe evolves. In the past, when the universe was smaller and denser, the Hubble constant was larger. Expansion was faster. In the future, as dark energy dominates more and more, the Hubble constant will approach a fixed value, and expansion will settle into an exponential pattern. Cosmologists describe the expansion using a quantity called the scale factor, usually denoted by the letter A. This scale factor tells you how much the universe has grown. If we set the scale factor to 1 right now, then in the past, when the universe was smaller, the scale factor was less than 1. In the future, when the universe is larger, the scale factor will be greater than 1. The rate of change of the scale factor is related to the Hubble constant, and the acceleration of the scale factor is related to dark energy. Using Einstein's equations of general relativity, combined with observations of the universe's contents, matter, radiation, dark matter, and dark energy, cosmologists can calculate how the scale factor changes over time. They can model the entire history of cosmic expansion from the Big Bang to the present and project into the future. These models tell us that expansion started incredibly fast during a period called inflation in the first fraction of a second after the Big Bang. Then, expansion slowed down as gravity from matter pulled back against it. This slowing continued for billions of years. But about 6 billion years ago, dark energy started to dominate. The repulsive effect of dark energy overcame the attractive pull of gravity, and expansion started to accelerate. It's been accelerating ever since, and it will continue to accelerate as long as dark energy remains constant. And here's where the math leads to something profound. In a universe with accelerating expansion, there's a maximum distance to which we can send a signal and have it arrive. That's the cosmic event horizon we talked about earlier. But there's also something called the particle horizon, which is the maximum distance from which light could have reached us by now. This is essentially the radius of the observable universe. These two horizons are different. The particle horizon is larger than the event horizon. We can see farther than we can signal. There are galaxies we can observe, galaxies whose ancient light is reaching us now, but to which we can never send a signal they'll receive. We can see them, but we can't reach them. They're visible ghosts, images from the past of places we can never touch. And the gap between these two horizons is growing. More and more of the observable universe is moving beyond our ability to influence or communicate with. We're becoming cosmically isolated. Now let's think about this from an alien perspective. Imagine an advanced civilization in a galaxy far away, beyond our cosmic event horizon. They arose billions of years ago, perhaps when the universe was younger and expansion was slower. They developed technology, learned physics, studied the cosmos, and eventually discovered cosmic expansion just as we did. They measured their Hubble constant, mapped their observable universe, and realized that most galaxies were receding beyond their reach. They sent out signals anyway, broadcasting into the cosmos, hoping to contact other civilizations. They knew most of their signals would never be received because the destinations were receding too fast. But they sent them anyway, covering as much of the reachable universe as they could. Some of those signals might have reached other civilizations. Brief moments of contact, exchanges of information across millions of light years and millions of years of time. Knowledge shared between civilizations that would never meet, never see each other, exist in the same cosmic epoch only briefly before being separated by the expansion of space. And eventually, that civilization looked out at the universe and realized they were alone. Every other galaxy had receded beyond their horizon. They could see the ancient light from distant galaxies, images from billions of years ago, but they knew those galaxies were now unreachable. The signals they'd sent in the distant past might have arrived by now, or they might have been swallowed by expansion, never making it across the growing voids. There was no way to know, and there was nothing they could do but watch as the universe emptied around them. Watch as the galaxies faded from view, their light stretched and redshifted until it became undetectable. Watch as the cosmic microwave background cooled and faded. Watch as the evidence of the Big Bang slowly erased itself. This is the future of our universe, and it's the present for any civilization that exists long enough. Cosmic isolation is inevitable in an accelerating universe. Unless dark energy changes, unless the acceleration reverses somehow, every civilization will eventually find itself alone. This has profound implications for the Fermi paradox, the famous question, where is everybody? If the universe is old and vast, and if life and intelligence are reasonably common, then we should see evidence of alien civilizations everywhere. We should see megastructures, modified stars, engineered planets, radio signals, something. But we see nothing. The universe appears empty, silent, dead. Many explanations have been proposed for this paradox. Maybe life is rare. Maybe intelligence is rare. Maybe civilizations destroy themselves before they can spread. Maybe they're hiding. Maybe they're here and we just don't recognize them. But cosmic expansion offers another explanation. Maybe civilizations exist, have always existed, in great numbers throughout the universe, but they're too far apart, separated by cosmic expansion, unable to reach each other despite their best efforts. Each civilization arises, develops, looks out at the universe, and finds itself alone. They send signals that never arrive. They build ships that can never complete the journey. They watch as the galaxies recede beyond reach, and eventually they accept their isolation. The universe could be teeming with intelligent life, millions or billions of civilizations, all of them alone, all of them wondering where everyone else is, never realizing that the answer is, they're out there, but space itself keeps us apart. This explanation has a certain elegance. It doesn't require life to be rare, or civilizations to be self-destructive. It just requires the universe to be large and expanding, which we know it is. And it explains not just why we don't see aliens nearby, but why we don't see them anywhere. Because the ones far away literally cannot reach us, and we cannot reach them. The barrier is fundamental, built into the structure of space itself. Now, let's consider what this means for the future of humanity, or any civilization that survives long enough. If we spread beyond Earth, if we colonize the solar system, the galaxy, eventually the local group, will face a choice. Do we try to send expeditions to other galaxy clusters before they recede beyond reach? The Virgo cluster, the Fornax cluster, the Coma cluster, these are massive collections of thousands of galaxies, rich in stars and potential habitable planets. But they're receding. Every year, they get farther away. Every year, the journey becomes harder. There will come a point where launching an expedition becomes impossible because the destination is receding faster than we can travel. We'd have to make the decision soon, on cosmic timescales, within the next few billion years, or miss the opportunity forever. And even if we launched expeditions successfully, even if ships left the Milky Way and traveled for millions of years across the growing voids between galaxy clusters, what would happen when they arrived? They'd establish colonies, civilizations in distant clusters, separated from us by hundreds of millions of light years. Those civilizations would be completely independent. They'd develop their own cultures, their own technologies, their own destinies, and they'd be cut off from us. Communication would be possible for a while, messages taking hundreds of millions of years to cross the distance. But eventually, as expansion accelerates, even communication would become impossible. The colonies would drift beyond our cosmic event horizon. We'd lose contact permanently. They'd become separate civilizations in separate bubbles of space, never to meet again. Humanity, or whatever we become, would fragment into isolated branches, each evolving separately, potentially for trillions of years. Some branches might thrive, others might fail. We'd never know. They'd never know about us. The universe would contain multiple human-derived civilizations, none aware of the others, each thinking themselves alone. This is the strange fate that cosmic expansion creates. Not destruction, not death, but isolation. Separation on scales so vast that connection becomes physically impossible. And here's perhaps the strangest part of all. This isolation might already be affecting us without our knowledge. The cosmic microwave background, the afterglow of the Big Bang, shows us the universe as it was about 380,000 years after the beginning. This radiation has been traveling toward us for over 13 billion years, stretched by expansion from visible light to microwave frequencies. When we study the cosmic microwave background, we see tiny fluctuations in temperature, slight differences from one direction to another. These fluctuations represent density variations in the early universe, seeds that eventually grew into galaxies and galaxy clusters. But there's something odd about these fluctuations. They're remarkably uniform on large scales. Regions of the cosmic microwave background that are separated by more than a few degrees on the sky are too far apart to have ever been in contact with each other. Light hasn't had time to travel between them, not in the 380,000 years between the Big Bang and the emission of the cosmic microwave background. So how did these widely separated regions end up with almost exactly the same temperature? How did they know to be so similar if they could never communicate, never exchange energy or information? This is called the horizon problem, and it's one of the puzzles that led to the theory of cosmic inflation. Inflation proposes that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, growing by a factor of at least 10 to the 26 in about 10 to the negative 32 seconds. This expansion was much faster than light, driven by a special field that permeated space at extremely high energies. During inflation, regions that were once close enough to be in thermal contact were stretched apart to vast distances. After inflation ended, they were separated by more than light could travel, but they retained the same temperature because they started from the same initial state before inflation separated them. This solves the horizon problem and explains why the cosmic microwave background is so uniform. But it also means that the observable universe is just a tiny patch of a much larger whole. During inflation, space expanded so fast that most of the universe was pushed beyond our cosmic horizon. There are vast regions of space, potentially infinite regions, that inflated away from us and are now so far away that we can never see them. They're beyond the observable universe, beyond the particle horizon, beyond any possibility of detection. And those regions might be completely different from what we see. Inflation was a quantum process, driven by random fluctuations in a field. Different regions of space underwent different amounts of inflation, ended inflation at different times, had different outcomes. Some regions might have inflated more and become larger. Some might have inflated less and remained smaller. Some might have different physical constants, different particle physics, different laws of nature. We can only observe our local patch, the part that inflated together and ended up with the properties we see. But beyond our horizon, the universe might be radically different. And we can never know because those regions are forever beyond our reach, separated from us, not by distance in the normal sense, but by the sheer amount of expansion that occurred during inflation. This connects back to our discussion of aliens in a profound way. If inflation created vast regions of space with different properties, then the question of whether aliens exist becomes much more complicated. Maybe life is common in our local patch of the universe, the region we can observe, but rare or impossible in other patches with different physics. Maybe there are patches where life is far more common, where every star has inhabited planets, where intelligence arises easily and civilizations spread throughout their local volumes. But we can never meet those civilizations because they're in a different patch of the inflated universe, beyond our horizon, separated from us by a gap that no signal can cross and no ship can traverse. The universe might be full of life, unimaginably full, but distributed in pockets that can never interact, can never even know about each other. Each pocket, each post-inflation bubble, isolated by the very process that created it. And our pocket, the observable universe, might be relatively empty, just by chance. Just because the quantum fluctuations that seeded galaxy formation happened to produce relatively few habitable worlds here. In another pocket, the dice rolled differently, and civilizations are everywhere. But we'll never know. The evidence is beyond our horizon, and it always will be. Let's return to something more concrete, the expansion rate itself. We've talked about the Hubble constant, 70 kilometers per second per megaparsec, or about 43 miles per second per megaparsec. But how do we actually measure this? How do we know the universe is expanding at all, let alone accelerating? The evidence comes from several independent sources, all of which agree remarkably well. The story begins in the 1920s, with Edwin Hubble working at the Mount Wilson Observatory in California. Hubble had access to the largest telescope in the world at the time, the 100-inch Hooker telescope. He used it to study nebulae, fuzzy patches of light scattered across the sky. Some astronomers thought these nebulae were clouds of gas within the Milky Way. Others argued they were separate galaxies, island universes far beyond our own galaxy. The debate had raged for years. Hubble settled it by discovering something remarkable. He found Cepheid variable stars in some of the nebulae, particularly in the Andromeda Nebula. Cepheid variables are stars that pulse regularly, brightening and dimming over periods of days or weeks. Henrietta Leavitt had discovered in the early 1900s that there's a relationship between a Cepheid's period and its intrinsic brightness. Longer period Cepheids are intrinsically brighter. If you measure the period, you know the true brightness. If you know the true brightness and measure the apparent brightness, you can calculate the distance using the inverse square law of light. Hubble measured Cepheids in Andromeda and calculated that it was about 900,000 light-years away. That's much farther than the size of the Milky Way, which was known to be about 100,000 light-years across. Andromeda had to be a separate galaxy. Modern measurements put Andromeda at about 2.5 million light-years, so Hubble's estimate was low, but he was right about the fundamental point. Nebulae were galaxies, and the universe was much larger than anyone had imagined. But Hubble didn't stop there. He started measuring distances to more galaxies using Cepheids and other techniques. And he noticed something strange. Almost all galaxies showed redshift in their spectra. The spectral lines were shifted toward longer wavelengths, toward the red end of the spectrum. Redshift happens when a light source is moving away from you. It's the Doppler effect for light. The faster the source is receding, the larger the redshift. Hubble plotted galaxy distances against their redshift, or equivalently, against their recession velocities. He found a linear relationship. The farther away a galaxy was, the faster it was receding. Double the distance, double the recession velocity. This was published in 1929 and became known as Hubble's law. It was direct evidence that the universe is expanding. Every galaxy is moving away from every other galaxy, carried by the expansion of space itself. The proportionality constant in Hubble's law is the Hubble constant, now denoted h0. Hubble's original estimate was about 500 kilometers per second per megaparsec, or about 310 miles per second per megaparsec, much too high. He had underestimated the distances to galaxies. Over the following decades, astronomers refined the distance measurements, improving the calibration of the cosmic distance ladder. The distance ladder is a series of techniques that build on each other. You measure distances to nearby stars using parallax. You use those stars to calibrate Cepheid variables. You use Cepheids to measure distances to nearby galaxies. You use those galaxies to calibrate brighter standard candles like supernovae. You use supernovae to measure distances to very distant galaxies. Each rung of the ladder depends on the rung below it, so errors accumulate. Small errors in nearby measurements become larger errors in distant measurements. This is why measuring the Hubble constant accurately has taken so long. By the 1990s, most measurements put the Hubble constant somewhere between 50 and 80 kilometers per second per megaparsec, or about 31 and 50 miles per second per megaparsec. The uncertainty was large enough that cosmologists joked about the Hubble constant being known to within a factor of 2. Then, in the late 1990s, two teams of astronomers set out to measure how expansion was changing over time. They expected to find that expansion was slowing down. Gravity from all the matter in the universe should pull back against expansion, decelerating it. The question was how much. Measuring the deceleration would tell you the total amount of matter in the universe and determine whether the universe would expand forever or eventually collapse. Both teams used Type Ia supernovae as standard candles. These are explosions of white dwarf stars that have accreted too much mass from a companion star. When the white dwarf exceeds a critical mass limit, about 1.4 times the mass of the Sun, it collapses and explodes in a thermonuclear runaway. The explosion reaches a peak brightness that's remarkably consistent from one supernova to another. With some corrections for variations in the light curve shape, you can use Type Ia supernovae as nearly perfect standard candles. The teams searched for supernovae in distant galaxies, measured their peak brightness, measured their redshift, and calculated their distances. Then they compared those distances to what they expected based on the measured redshift. If expansion had been slowing down, distant supernovae should appear brighter than expected because they're closer than they would be in a universe with constant expansion. Instead, the supernovae appeared dimmer. They were farther away than expected. Expansion hadn't been slowing down. It had been speeding up. The universe's expansion is accelerating. This discovery was announced in 1998 and was met with shock and skepticism. Accelerating expansion made no sense based on known physics. Gravity should slow expansion, not speed it up. Something else had to be pushing, and that something became known as dark energy. The discovery earned the leaders of both teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. Since then, many independent observations have confirmed the accelerating expansion. The cosmic microwave background measurements from satellites like WMAP and Planck agree. Observations of baryon acoustic oscillations, subtle patterns in galaxy clustering that serve as a cosmic ruler, agree. Observations of gravitational lensing, how galaxy clusters bend light from more distant objects, agree. All the evidence points to the same conclusion. The universe is not only expanding, but expansion is getting faster. Dark energy is real, whatever it is, and its effects are growing over time as matter becomes more dilute and dark energy comes to dominate the universe's energy budget. This leads to the future we've been discussing, a universe where distant galaxies accelerate away, crossing the cosmic event horizon, leaving us increasingly isolated. A universe where the volume we can interact with shrinks even as the total universe grows. A universe headed toward a cold, dark, empty future where each gravitationally bound structure is alone in an infinite void. Understanding this future requires understanding expansion and dark energy. And understanding those requires understanding the observations and measurements that revealed them. The Hubble constant, the supernova data, the cosmic microwave background, these aren't just abstract numbers. They're our window into the fundamental nature and fate of the cosmos. We've talked about the Hubble constant, 70 kilometers per second per megaparsec, or about 43 miles per second per megaparsec. But how do we actually measure this? How do we know the universe is expanding at all, let alone accelerating? The evidence comes from several independent sources, all of which agree remarkably well. First, there's the redshift of galaxies. When we look at the spectrum of light from a distant galaxy, we see familiar patterns, absorption and emission lines from hydrogen, helium, and other elements. But these patterns are shifted toward longer wavelengths compared to the same patterns measured in laboratories on Earth. This shift is called redshift, and it's caused by the expansion of space, stretching the light waves as they travel. The farther away a galaxy is, the more time its light has spent traveling through expanding space, and the more it's been stretched, producing a larger redshift. By measuring redshifts and distances for many galaxies, we can plot the relationship between distance and recession velocity. This relationship, the Hubble law, is a straight line, exactly what you'd expect from uniform expansion. Second, there are standard candles, objects with known intrinsic brightness. If you know how bright something really is, and you measure how bright it appears, you can calculate how far away it is. The most useful standard candles for cosmology are Type Ia supernovae, exploding white dwarf stars that all reach approximately the same peak brightness. By observing Type Ia supernovae in distant galaxies, measuring their apparent brightness and their redshift, we can map out the expansion history of the universe. This was how dark energy was discovered. Astronomers expected distant supernovae to be slightly brighter than predicted if expansion was slowing down. Instead, they were dimmer, meaning they were farther away than expected, meaning expansion had accelerated. Third, there's the cosmic microwave background. The detailed pattern of fluctuations in this ancient radiation tells us about the geometry of the universe, the amounts of matter and dark energy, and the rate of expansion both now and in the past. By analyzing the cosmic microwave background, cosmologists can measure the Hubble constant and other cosmological parameters with high precision. All these methods agree. The universe is expanding, expansion is accelerating, and the rate of expansion is consistent with about 70 kilometers per second per megaparsec, or about 43 miles per second per megaparsec. The agreement between independent methods is one of the great triumphs of modern cosmology. But there's a wrinkle. Recently, different methods have started to give slightly different values for the Hubble constant. Measurements using the cosmic microwave background give a value around 67 kilometers per second per megaparsec, or about 42 miles per second per megaparsec. Measurements using Type Ia supernovae and other local methods give a value around 73 kilometers per second per megaparsec, or about 45 miles per second per megaparsec. The difference is small, less than 10%, but it's statistically significant. It's unlikely to be just measurement error. This discrepancy is called the Hubble tension, and it's one of the most exciting puzzles in cosmology right now. It might mean we're making a subtle mistake in one of the measurement methods. Or it might mean our cosmological model is incomplete, that there's some new physics we haven't accounted for. Maybe dark energy isn't constant, but changes over time. Maybe there are additional components to the universe we haven't detected. Maybe the early universe was different from what we think. Resolving the Hubble tension is a major goal of current research, and the answer, whatever it is, will deepen our understanding of cosmic expansion. But regardless of the exact value, the basic fact remains. The universe is expanding, and it's expanding fast enough to separate distant regions permanently. Now, let's think about the psychology of all this. How should we, as a species, as individuals, feel about cosmic expansion and the isolation it creates? On one hand, it's profoundly lonely. The universe might be full of life, full of civilizations, but most of them are forever beyond our reach. We might be surrounded by intelligence, by cultures and stories and perspectives we could learn from, but we'll never make contact. We'll never exchange ideas, never collaborate, never even know they exist. That's a kind of loneliness that's hard to comprehend. It's not just being alone in a room or a city. It's being alone in the sense that the vast majority of the universe is fundamentally inaccessible, sealed off by the expansion of space itself. Consider what this means in concrete terms. Right now, there might be a civilization in a galaxy 1 billion light-years away. They might have developed technology, art, music, literature, philosophy. They might have solved problems we're still struggling with. They might have answers to questions about the nature of consciousness, the origin of life, the meaning of existence. They might have discovered physics beyond our current understanding, technologies that seem like magic to us. And we'll never know. We'll never have access to their knowledge, their perspective, their achievements. They might as well not exist as far as we're concerned. The information barrier is absolute, and the same is true from their perspective. If they're looking out at the universe, wondering if they're alone, looking for signs of other civilizations, they might have detected us in some way. They might have seen the oxygen in Earth's atmosphere, a sign of photosynthetic life. They might have detected radio signals we've been broadcasting for the past 100 years, though those signals have only traveled 100 light years so far, a tiny distance on cosmic scales. But even if they know we exist, they can never reach us. They can never send a probe, never visit, never exchange anything more than the most basic information via electromagnetic signals. And even those signals are limited. They take 1 billion years to travel the distance. By the time their message reaches us, we might be gone. By the time our reply reaches them, they might be gone. The conversation is impossible in any meaningful sense. This creates a strange paradox. The universe might be full of intelligence, but each intelligent species is effectively alone, able to detect others, perhaps, but never to interact in ways that matter. It's like being in a crowded room where everyone is sealed in soundproof boxes. You can see that others are there, but you can't communicate, can't touch, can't connect. You might wave, and they might wave back, but that's the extent of it. The isolation is complete, even in the presence of others. Some philosophers and scientists have argued that this isolation might actually be beneficial. If contact between civilizations were easy, if the universe were small enough that advanced civilizations could travel freely between stars and galaxies, the result might be conflict. Different civilizations would compete for resources, for territory, for dominance. Wars might erupt on galactic scales. One civilization might try to conquer or destroy others. The history of human civilization is full of examples of what happens when cultures with different levels of technology meet. Usually, the more advanced culture dominates, sometimes peacefully, often not. If the same pattern holds on cosmic scales, then easy contact between civilizations might lead to cosmic-scale conflict. The Fermi paradox would have a dark answer. We don't see evidence of alien civilizations, not because they're rare, but because they destroy each other, or because one dominant civilization has already conquered everyone else. Cosmic expansion prevents this. It creates natural barriers that no amount of technology can overcome. Each civilization gets its own protected territory, its own bubble of space, guaranteed by the laws of physics. You might not like your neighbors, but you don't have to worry about them invading because they literally can't reach you. This enforced isolation might be what allows intelligent life to survive long-term. Instead of fighting over the universe, each civilization gets a piece of it, large enough to explore and develop for billions of years, but separated from others by impassable voids. It's not perfect, but it might be necessary. Another perspective comes from thinking about information. One of the great dreams of science and philosophy is to understand everything, to have complete knowledge of the universe. But cosmic expansion makes this impossible. There are parts of the universe we can never observe, never study, never understand. The information they contain is beyond our reach, sealed off by the cosmic event horizon. This means our knowledge will always be incomplete. We can study our local patch of the universe in great detail. We can map every galaxy in the local group, study every star, catalogue every planet. We can understand the physics that governs this region, the history that led to its current state, the processes that shape its evolution. But we can't extend that understanding to the entire universe. We can't know if other regions have the same properties, the same history, the same outcomes. We can make assumptions, we can build models, but we can't test those models against the full range of cosmic variation. Our theories will always be limited to what we can observe, and what we can observe is just a tiny fraction of what exists. This is frustrating for scientists and philosophers who want complete understanding. But it's also liberating in a way. It means there will always be mysteries, always be unknowns, always be frontiers beyond which we cannot pass. The universe will never be fully mapped, fully understood, fully catalogued. There will always be more to wonder about, more to imagine, more to dream about. The cosmic event horizon is a boundary on our knowledge, but it's also a permanent source of mystery and wonder. And maybe that's valuable. Maybe a universe that we could fully understand, fully explore, fully catalogue would be boring. Maybe the fact that there are limits, that there are horizons we can't cross, is what keeps the universe interesting. It guarantees that no matter how much we learn, there's always more. No matter how far we travel, there's always farther. No matter how deep we dig into the nature of reality, there's always another layer. On the other hand, there's something strangely freeing about this. If we're truly isolated, if contact with distant civilizations is impossible, then we don't have to worry about invasion, about hostile aliens, about competition for resources on galactic scales. Our local group of galaxies, the Milky Way and its neighbors, is ours. It's a vast territory, thousands of galaxies, trillions of stars, more worlds than we could ever explore or inhabit. And it's safe, protected by the natural barrier of cosmic expansion. No empire from a distant galaxy cluster can conquer us because they can't reach us. No alien armada can cross the expanding void. We're free to develop at our own pace, to explore our own corner of the universe without interference. Let's put some numbers on this to understand just how vast our local territory actually is. The Milky Way alone contains between 200 billion and 400 billion stars. That's 2 to 4 times 10 to the 11th stars. Each one is a potential solar system, potentially with planets, potentially with the conditions for life. If just 1% of those stars have planets in the habitable zone, that's 2 to 4 billion potentially habitable worlds in our galaxy alone. If 1% of those actually develop life, that's 20 to 40 million living worlds. If 1% of those develop intelligent life, that's 200,000 to 400,000 potential civilizations. And that's just the Milky Way. Andromeda, our nearest large galactic neighbor, is even bigger, containing about 1 trillion stars. That's 1 times 10 to the 12th stars, more than twice as many as the Milky Way. If we apply the same percentages, Andromeda might contain up to 1 million intelligent civilizations. The Triangulum Galaxy, the third largest member of our local group, contains about 40 billion stars. That's still a huge number, potentially hosting tens of thousands of civilizations if life is reasonably common. Add in all the dwarf galaxies in our local group, there are more than 80 of them, and you're looking at a total of roughly 1.5 trillion stars. All of these are within our reachable universe. All of them are gravitationally bound to us, not receding beyond the event horizon. If intelligent life exists anywhere in this vast collection of galaxies, we could potentially detect them, communicate with them, perhaps even visit them, given enough time and technology. The challenge wouldn't be cosmic expansion, it would be distance in the ordinary sense. Andromeda is 2.5 million light-years away. A signal sent there at light speed would take 2.5 million years to arrive. A reply would take another 2.5 million years to return. That's a 5 million year round trip, communication time. It's almost incomprehensibly long, but it's not impossible. A spacecraft traveling at 10% of light speed, which is conceivably achievable with advanced propulsion systems, would take about 25 million years to reach Andromeda. That's longer than the entire existence of the human genus. Longer than the time since our ancestors split from the ancestors of other great apes. But it's finite. It's a real number. It's not infinite, not impossible, just very, very difficult and very, very slow. Compare this to a galaxy 1 billion light-years away. Even if you could travel at 99.9% of light speed, you'd be fighting against cosmic expansion the entire way. The destination would be receding almost as fast as you're approaching. You'd make minimal progress, burning enormous amounts of energy, traveling for billions of years, and never arriving. The difference is fundamental. Distance alone can be overcome with time and technology. Distance plus expansion cannot. This raises interesting questions about strategy. If humanity survives long enough to contemplate interstellar or intergalactic exploration, should we focus our efforts on our local group? Should we try to explore and colonize as many star systems within the Milky Way and Andromeda as possible? Or should we send missions to more distant galaxy clusters before they recede beyond reach? The answer depends on timescales and priorities. Within the Milky Way, we have billions of years to explore. The galaxy isn't going anywhere. It will still be here, accessible, billions of years from now. The same is true for the local group. Andromeda will actually get closer over the next few billion years as the two galaxies approach their eventual merger. So there's no urgency from a cosmic expansion standpoint. We can take our time, develop technology gradually, spread slowly through the galaxy without worrying that our destination will become unreachable. But galaxy clusters beyond the local group are receding. The Virgo cluster, the Fornax cluster, the Coma cluster, all of them are getting farther away every second. Right now, they're still reachable. A civilization with sufficient technology could send expeditions to these clusters, and those expeditions would eventually arrive. But there's a deadline. At some point in the future, as expansion accelerates, these clusters will recede beyond the cosmic event horizon. After that, no expedition can reach them, no matter how fast it travels. The window is closing. Current estimates suggest we have tens of billions of years before the nearest galaxy clusters become unreachable. That sounds like a lot of time, and it is. But on cosmic timescales, it's not unlimited. If humanity wants to establish a presence in those distant clusters, we'd need to act, cosmically speaking, soon. We'd need to develop the technology for intergalactic travel, build the ships, launch the missions, all within a few tens of billions of years. After that, the opportunity is gone forever. This creates a strange sort of cosmic pressure. Not immediate, not urgent in human terms, but real nonetheless. The universe is giving us a time limit. We can spread through our local group at our leisure, but if we want to go farther, we need to do it before the door closes. And once it closes, it never reopens. The civilizations we might establish in distant galaxy clusters would be cut off from us permanently, evolving independently, developing their own cultures and technologies, never able to return home or even communicate with us after a certain point. They'd become separate branches of the human family tree, isolated by cosmic expansion. Now, let's think about what this means for the search for extraterrestrial intelligence in more detail. SETI, the search for extraterrestrial intelligence, has been ongoing since the 1960s. The basic idea is to listen for radio signals from space that might be artificial, created by alien civilizations trying to communicate. We've scanned millions of star systems, listened to billions of radio frequencies, analyzed countless hours of data. And we've found nothing. No signals, no messages, no evidence of alien technology. The universe, as far as we can tell from our searches so far, is silent. This silence is called the Great Silence, and it's at the heart of the Fermi paradox. If life is common, if intelligent civilizations should be plentiful, why don't we hear anything? Cosmic expansion offers a partial answer. If most civilizations are beyond our cosmic event horizon, we wouldn't hear from them, even if they're broadcasting. Their signals can't reach us because space is expanding, faster than light can cross it. But this doesn't explain the silence from nearby stars. The Milky Way has hundreds of billions of stars, and expansion doesn't affect our galaxy. If even a tiny fraction of those stars host intelligent life, we should be detecting signals. But we're not. Maybe life is rarer than we think. Maybe the jump from simple life to intelligent, technological life is extremely difficult and happens only rarely. Maybe Earth is unusual, the product of an unlikely chain of events that doesn't repeat often. Maybe intelligence is common, but civilizations don't last long. Maybe they destroy themselves through war, environmental collapse, or other catastrophes before they can spread and make their presence known. Maybe they're quiet on purpose, either hiding from potential threats or simply not bothering to broadcast because they don't expect anyone to be listening. Or maybe they're using communication methods we don't recognize. Radio signals are just one small part of the electromagnetic spectrum, and they're the method we happen to use because it's what we developed first. But a more advanced civilization might use different technologies entirely. They might communicate via neutrinos, gravitational waves, quantum entanglement, or methods we haven't even discovered yet. If so, we could be surrounded by alien communications and not recognize them because we're looking in the wrong place, listening on the wrong channel. Cosmic expansion adds another layer to this puzzle. Even if civilizations are broadcasting, even if they're using radio or other electromagnetic signals, those signals weaken over distance. The farther they travel, the more spread out they become, the harder they are to detect. And if they have to cross expanding space, they get redshifted, stretched to longer wavelengths, weakened even more. A powerful signal from a civilization a billion light-years away might be so weak and so redshifted by the time it reaches us that it's indistinguishable from background noise. We might be receiving alien signals right now without knowing it, because they're too faint, too distorted, too buried in the cosmic radio background to detect. This is why SETI focuses primarily on nearby stars. The searches target star systems within a few hundred light-years. distances where signals would still be strong enough to detect with our current technology. But even within the Milky Way, there are limiting factors. The galaxy is about 100,000 light-years across. A signal from the far side would take 100,000 years to reach us. If a civilization on the far side of the galaxy started broadcasting 100,000 years ago, we might be receiving their signals right now. But if they only broadcast for 1,000 years and then stopped, maybe they destroyed themselves. Maybe they just lost interest. We'd only detect their signals during that narrow window of time. If we weren't listening during that window, we'd miss them entirely. The universe could be full of civilizations that existed, broadcast briefly, and then went silent before their signals reached us or while we weren't paying attention. We'd never know they were there. This temporal dimension makes the search even harder. It's not just about where civilizations are in space, but when they exist in time. Two civilizations could be separated by only a few thousand light-years, close enough that communication should be possible. But if one arises and falls before the other, develops radio technology, they'll never make contact. The timing has to align, and the more civilizations there are, the less likely perfect alignment becomes. Think of it like two ships passing in the night. If one ship is traveling north and the other is traveling south, they might pass close to each other geographically. But if they pass at different times, if one goes through a location in the morning and the other passes through the same location in the evening, they never see each other, even though they were in the same place. The same thing can happen with civilizations in space and time. Another factor to consider is the direction of broadcasts. We've been sending radio signals into space for about 100 years, since the invention of radio. But we haven't been trying to send messages to aliens for most of that time. Most of our radio signals are incidental, leakage from television broadcasts, radar systems, communications networks, not intentional messages to other stars. These signals spread out in all directions, weakening rapidly. By the time they've traveled even a few dozen light-years, they're so weak that detecting them would require enormous radio telescopes and very sensitive receivers. An alien civilization would need to be specifically looking in our direction, using powerful equipment to have any chance of detecting our accidental leakage. If they're not looking, if their attention is elsewhere, they'd miss us entirely, even if they're close by. The same is true in reverse. If alien civilizations exist and they're broadcasting, they might not be broadcasting in our direction. They might be aiming their signals at other stars, other regions of the galaxy where they think life is more likely. We might be outside their search area, irrelevant to their strategy, never targeted by their broadcasts. Or they might have stopped broadcasting altogether. There's a concept in SETI called the broadcast window, the period of time during which a civilization actively sends signals into space. For humans, that window opened about 100 years ago and might close at some point in the future. If we develop more efficient communication methods that don't leak into space, if we switch from radio to fiber optics or laser communications or quantum links, our radio broadcasts might stop. Future humans might communicate extensively, but without emitting detectable radio signals. If that happens, our broadcast window might only last a few hundred years. Alien civilizations might have similar windows. They might broadcast for a while, then stop when they develop better technologies or lose interest. If the average broadcast window is only a few hundred or a few thousand years, and civilizations are separated by thousands or tens of thousands of light years, the chances of two broadcast windows overlapping at the right time become very small. Halo, we might be surrounded by civilizations that broadcasted in the past or will broadcast in the future, but aren't broadcasting now during the brief period when we're listening. All of these factors, distance, expansion, time, direction, broadcast windows, combine to make the search for extraterrestrial intelligence incredibly difficult. It's like trying to find someone in a vast, dark forest where everyone is moving. Everyone has a flashlight, but only turns it on occasionally. And everyone is shouting, but only in certain directions for brief periods. The chances of two people finding each other become vanishingly small, even if the forest is crowded. There's also something humbling about understanding cosmic expansion. It reminds us that the universe doesn't care about our ambitions or our curiosity. It's not designed for easy exploration. It's not set up to facilitate communication between civilizations. It simply exists, following the laws of physics, expanding because that's what the equations say it does. Our desires to meet aliens, to explore the cosmos, to understand everything, these are our desires, not the universe's purpose. And the universe is under no obligation to make those desires achievable. This connects to a deeper question about the role of consciousness in the universe. We are, as far as we know, the only part of the universe that is aware of itself. The only matter that has organized itself into thinking, feeling, observing beings capable of understanding the cosmos. Stars don't know they're stars. Galaxies don't know they're galaxies. Black holes don't contemplate their own existence. But we do. We look out at the universe, measure it, study it, comprehend it, at least partially. We're the universe, becoming aware of itself. And cosmic expansion puts limits on what we can become aware of. There are parts of the universe beyond the cosmic event horizon that we can never observe, never study, never understand. The information they contain is forever beyond our reach. This raises a philosophical question. If a tree falls in a forest and no one is there to hear it, does it make a sound? If a galaxy exists beyond the cosmic event horizon, beyond all possible observation, does it exist in any meaningful sense? Not to us, certainly. It can never affect us, never influence our observations, never enter into our theories or our understanding. For all practical purposes, it doesn't exist as far as we're concerned. But it might exist from some other perspective. Another civilization in another part of the universe might be able to observe that galaxy. From their perspective, it exists. It's part of their observable universe, even if it's not part of ours. This means the universe is fundamentally observer-dependent. What exists depends on where you are, when you are, what you can observe. Different observers will have different observable universes, different cosmic event horizons, different limits on what they can know. There's no God's eye view, no perspective from which you can see everything. Every observer is limited to their own bubble of space, their own cosmic horizon. And those bubbles don't necessarily overlap. You and I, standing on Earth right now, share the same observable universe because we're in the same place. But a civilization in a distant galaxy has a different observable universe. Some galaxies we can see, they can't. Some galaxies they can see, we can't. Our knowledge of the universe is fundamentally partial, fundamentally limited by our location and the finite speed of light and the expansion of space. This has implications for the very concept of physical law. We formulate laws of physics based on observations. We observe how matter behaves, how energy flows, how forces work. We create mathematical descriptions of these patterns. We test those descriptions with experiments and observations. When they match, we call them laws of physics. But those laws are based on observations within our observable universe. We have no way of knowing if the same laws apply beyond our cosmic horizon. Maybe they do. Maybe the laws of physics are truly universal, the same everywhere, even in regions we can never observe. Or maybe they're not. Maybe different regions of space, especially regions that inflated separately during cosmic inflation, have different laws, different values of physical constants, different particles, different forces. We assume uniformity, but that assumption might be wrong. The universe might be far more varied, far stranger than we can ever know because the evidence is beyond our reach. This connects back to the multiverse idea. If cosmic inflation created many separate bubbles of space, each with potentially different physics, then the universe is not just large, it's fundamentally diverse. And most of that diversity is hidden from us, sealed off by expansion, existing in principle but unknowable in practice. From a philosophical standpoint, this is both humbling and fascinating. Humbling because it reminds us that our knowledge is limited, that there are things we can never know, questions we can never answer. Fascinating because it suggests the universe is far richer, far more complex than even our wildest theories imagine. We live in one small patch of reality, able to observe only a tiny fraction of what exists. The rest is out there, somewhere, beyond the horizon, unknowable but not non-existent. It's like being in a vast library where most of the books are locked away in rooms you can never enter. You can read the books in your section, learn from them, build understanding based on them. But you'll never know what's in the other sections, what knowledge they contain, what stories they tell. The library is larger than your accessible portion, but you can only work with what you have. Now let's think about what this means on a more personal, human level. We've been talking about cosmic scales, billions of years, billions of light years, concepts so vast they're hard to grasp emotionally. But cosmic expansion affects us here and now in subtle ways. It affects how we think about our place in the universe, our significance, our future. Consider that every moment, the universe is getting bigger. Space is stretching. Distant galaxies are receding. The cosmic event horizon is evolving, slowly shrinking as acceleration dominates. This is happening right now, continuously, inexorably. You can't see it or feel it because the effect is only significant on the largest scales. But it's real. The universe you inhabit now is slightly larger than the universe that existed 1 second ago. And it will be slightly larger, still, 1 second from now. This constant growth, this relentless expansion, this is the backdrop against which all of existence plays out. Stars form and die, galaxies collide and merge, life arises and evolves, all while space itself expands around everything. It's like a stage that's constantly getting bigger, slowly, imperceptibly, but never stopping. For most of human history, we didn't know this. We thought the universe was static, eternal, unchanging. The stars were fixed in their positions. The cosmos was permanent. Now, we know better. The universe is dynamic, evolving, headed toward a future that looks very different from the present. This knowledge changes things. It makes the universe feel less permanent, less solid. Everything is temporary, even the large-scale structure of the cosmos. The galaxies we see now will eventually disappear. The cosmic microwave background will fade to undetectable levels. The evidence of the Big Bang will erode away. Future observers, if any exist, will inhabit a very different universe, darker, emptier, more mysterious. They won't have the advantages we have. They won't be able to see the cosmic microwave background and infer the Big Bang. They won't be able to observe distant galaxies and measure cosmic expansion. They'll look out at an empty universe and draw wrong conclusions, thinking they live in a static, eternal cosmos, not knowing that galaxies once filled space, not knowing about the Big Bang, not knowing that their observable universe is just a local fragment of a much larger whole. They'll be cosmologically impoverished, lacking the evidence we have, unable to reconstruct the true history of the universe. In that sense, we're lucky. We live at a time when the universe still reveals its secrets. When the cosmic microwave background is still detectable, when distant galaxies are still visible, when the evidence of cosmic expansion and the Big Bang is still accessible. 100 billion years from now, that won't be true. The universe will have expanded so much, accelerated so dramatically, that almost all evidence of its origins and evolution will have disappeared beyond the horizon. Future civilizations, if any arise that late, will be trapped in ignorance, unable to learn what we've learned because the evidence will be gone. This is called the cosmological dark age, a future epoch when observational cosmology becomes impossible because there's nothing left to observe beyond the local galaxy. We're living in a golden age of cosmology, able to see farther back in time and farther out in space than any future civilization will be able to. This makes our moment in cosmic history special, not because we're at the center or because the universe was designed for us, but because we happen to exist at a time when understanding the cosmos is still possible, a few billion years earlier, and the universe would have been too young, too hot, too chaotic for complex life to exist. A few 100 billion years later, and the universe will be too old, too empty, too dark for its true nature to be discoverable. We're in the middle, in the narrow window when both life and cosmology are possible. That's worth appreciating. We live in a universe that's fundamentally indifferent to us, and cosmic expansion is one of the clearest demonstrations of that indifference. But perhaps most importantly, understanding cosmic expansion changes how we think about our place in the universe. For most of human history, we thought we were at the center of everything. Then we learned we're not. Earth orbits the sun orbits the galaxy is one of billions. We're not special in terms of location. Cosmic expansion adds another layer to this. Not only are we not at the center, but the part of the universe we can access is limited, temporary, shrinking. We're not just one planet among billions. We're one civilization, if there are others, isolated in a bubble of space that's getting smaller every moment. And yet, within that bubble, we have the capacity to understand what's happening. We can measure the expansion, calculate the event horizon, predict the future. We're small and isolated and temporary, but we're aware. We know where we stand, what we can reach, what we can't. That awareness is itself remarkable. The universe doesn't have to be comprehensible, but it is, at least in part. We've figured out the rules, understood the expansion, mapped the territory we can access. That's an achievement worth recognizing. Let me give you one more scenario to think about. Imagine humanity survives, not just for centuries or millennia, but for billions of years. We spread throughout the Milky Way, colonizing thousands or millions of star systems. We merge with Andromeda, and the other local group galaxies, creating a single massive galaxy full of inhabited worlds. We develop technology beyond anything we can currently imagine, extending our lifespans, enhancing our intelligence, building structures on scales we can barely conceive. And we turn our attention outward to the universe beyond our local group. We see the distant galaxy clusters, the Virgo cluster, the Coma cluster, the Hercules cluster, all receding away from us. We know that if we don't act soon, they'll recede beyond reach forever. So, we make a decision. We'll send expeditions, colony ships, not to a few galaxies, but to as many clusters as we can reach. Thousands of ships, each one carrying the seeds of a new civilization, each one aimed at a different galaxy cluster, hundreds of millions of light years away. These ships travel for millions of years, crossing the voids between clusters, arriving at their destinations long after everyone who built them has been gone for eons. They establish colonies, new civilizations, cut off from the Milky Way almost immediately by the expansion of space. And those civilizations spread, colonizing their local clusters, eventually facing the same choice we faced. Send more expeditions to even more distant clusters, or accept isolation. This process could continue, a wave of colonization spreading outward, racing against cosmic expansion, trying to fill as much of the reachable universe as possible before the event horizon shrinks too much. It's a race we're destined to lose eventually, because expansion is accelerating. But before we lose, we might seed civilizations across vast regions of space. Millions of separate branches of humanity, all isolated from each other, all evolving independently, none aware of the others. The universe would contain a diaspora of human-derived civilizations, scattered across billions of light years, separated by expansion, each one thinking itself alone, each one carrying a fragment of our legacy. And here's the profound part. From our perspective, right now, we might already be one of those fragments. Maybe an ancient civilization, billions of years ago when expansion was slower, spread throughout the universe. Maybe they sent colony ships to every reachable galaxy cluster. Maybe one of those ships arrived in the region that would become the Milky Way. Maybe life on Earth is a distant descendant of that ancient colony, so far removed in time that no memory remains, no record, no evidence, except the fact that we exist. And maybe there are other descendants, other branches of that ancient civilization, scattered throughout the universe, all of them isolated by expansion, all of them wondering if they're alone. We'd have no way to know. The evidence would have been erased by time and expansion. We could be one branch of a vast tree, completely unaware of the other branches, because they're beyond our cosmic horizon. This is speculation, of course. There's no evidence for ancient colonization or panspermia on cosmic scales. But it's not physically impossible. And it illustrates the strange possibilities that cosmic expansion creates. Isolation so complete that entire histories could be hidden, entire civilizations could exist unknown to each other, entire branches of life could evolve separately for billions of years without ever making contact. Let's bring this back to the present. What does cosmic expansion mean for us right now, today? In practical terms, not much. The expansion has no effect on our daily lives. It doesn't affect Earth's orbit, or the structure of the solar system, or the galaxy. It only matters on the largest scales, between galaxy clusters and beyond. But in terms of how we think about the universe and our place in it, it matters enormously. It tells us that the universe we can interact with is limited. It tells us that if aliens exist, most of them are beyond our reach. It tells us that the future of any long-lived civilization is isolation, not expansion without limit. It changes the questions we ask. Instead of, when will we make contact with aliens, we ask, are there any aliens within our reachable volume of space? Instead of, how far can we explore, we ask, what can we reach before it recedes beyond the event horizon? Instead of, what is the universe like, we ask, what is our local patch of the universe like? Understanding that other patches might be completely different and forever unknowable. These are harder questions, in some ways, more limited. But they're also more focused, more realistic. They acknowledge the constraints imposed by physics, by the structure of space itself. And they remind us that understanding the universe means understanding not just what exists, but what we can access and what we can know. Here's one final thought. The fact that cosmic expansion separates civilizations might actually be necessary for intelligent life to exist at all. Think about it this way. If the universe weren't expanding, if all the matter that exists now were compressed into a smaller space, the universe would be much denser. Galaxies would be closer together, stars would be packed more tightly, and the night sky would be bright with the light of countless nearby galaxies and stars. This is called Olber's paradox. In a static, infinite universe, every line of sight should eventually hit a star, making the entire sky as bright as the surface of a star. The fact that the night sky is dark tells us the universe is either finite or expanding, or both. We now know it's expanding. The expansion spreads things out, creating the darkness we see. But expansion does more than that. It also provides safety. If galaxies were packed closely together, they'd interact more often, colliding, merging, disrupting each other's structure. Star formation would be chaotic, stellar orbits would be unstable, and the conditions for life might be much rarer. The expansion gives galaxies room, allows them to evolve in relative isolation, creates stable environments where stars can form, planets can orbit, and life can develop over billions of years. In a very real sense, cosmic expansion might be one of the prerequisites for our existence. We might only be here, able to contemplate the universe, because expansion has created a calm, stable region of space where life can thrive. And the isolation that expansion creates, the barrier between distant civilizations, might be the price we pay for that stability. You can't have both. You can't have a densely packed universe full of galaxies interacting constantly and also have stable, long-lived planetary systems where complex life can evolve. Cosmic expansion gives us one or the other, and we happen to live in the universe where expansion wins, where isolation is the cost of existence. So when we look out at the universe and see those distant galaxies receding, when we calculate that most of them are beyond our reach, we might feel disappointed. We might wish the universe was smaller, denser, easier to explore. But if it were, we might not be here to wish for anything. The universe that allows us to exist is the same universe that keeps us apart from distant civilizations. It's a package deal, and we're living inside that package. We've covered a lot of ground tonight, from the basic fact of cosmic expansion to the profound implications for alien contact and the future of civilization. Let's recap the key points. The universe is expanding, and this expansion is accelerating due to dark energy. Space itself is growing, creating new distance between galaxies, and this growth is faster than any object can travel through space. Beyond a certain distance, called the cosmic event horizon, galaxies are receding faster than light. We can see some of them because their ancient light is still reaching us, but we can never send signals to them or travel to them. They're forever beyond our reach. This means that if alien civilizations exist in those distant galaxies, we can never meet them, no matter how advanced our technology becomes. The barrier isn't technological, it's fundamental, built into the structure of space itself. As expansion accelerates, more and more of the universe moves beyond the event horizon. The volume of space we can interact with is shrinking, even as the total universe grows. In the far future, every galaxy outside our local group will have disappeared beyond the horizon. Future observers will see an empty universe, no evidence of the Big Bang, no distant galaxies, just their local galaxy surrounded by darkness. This has profound implications for the Fermi paradox and the search for extraterrestrial intelligence. The universe might be full of civilizations, but they're separated by cosmic expansion, unable to reach each other, each one isolated in its own bubble of space. But let's dig deeper into the actual mechanics of why cosmic expansion works the way it does. What exactly is causing space to expand? Why is the expansion accelerating? And what does this tell us about the fundamental nature of the universe? The expansion of the universe is described by Einstein's equations of general relativity. These equations relate the geometry of spacetime to the distribution of matter and energy within it. In a universe filled with matter and energy, spacetime curves, and that curvature determines how the universe evolves over time. One of the solutions to Einstein's equations describes an expanding universe. Alexander Friedmann found this solution in 1922, just a few years after Einstein published General Relativity. Friedmann showed that a universe filled uniformly with matter cannot be static. It must either expand or contract. This was a shocking result because at the time, everyone, including Einstein, believed the universe was eternal and unchanging. The idea that it might be expanding or contracting seemed absurd. Einstein was so uncomfortable with this prediction that he modified his equations by adding a term called the cosmological constant. This term represented a repulsive force that could exactly balance gravity and keep the universe static. But then, Hubble discovered that galaxies are receding, that the universe really is expanding. Einstein called the cosmological constant his greatest blunder and removed it from his equations. Except it turns out the cosmological constant wasn't a blunder after all. We now know it was right, just for the wrong reason. There is a repulsive force in the universe, but it's not balancing gravity to keep things static. It's overwhelming gravity and causing expansion to accelerate. We call this force dark energy. Dark energy is the most mysterious component of the universe. We know it exists because we see its effects, but we don't know what it is. Current observations suggest that dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible stuff that holds galaxies together through its gravitational pull, makes up about 27%. Ordinary matter, the stuff that makes up stars, planets, and us, makes up only about 5%. We live in a universe where 95% of the content is stuff we don't understand. 68% is dark energy, pushing space apart. 27% is dark matter, pulling things together through gravity, but invisible to all electromagnetic radiation. Only 5% is the normal matter we can see and touch and study directly. This is humbling. We've learned an enormous amount about the universe in the past century. We've mapped the cosmic microwave background, detected gravitational waves, photographed black holes, discovered thousands of exoplanets. But the more we learn, the more we realize how much we don't know. The universe is dominated by two forms of stuff, dark matter and dark energy, that we can't directly detect, can't explain, and don't understand. So, what is dark energy? The simplest explanation is that it's the energy of empty space itself. Quantum mechanics tells us that empty space isn't really empty. It's filled with quantum fields that fluctuate even in vacuum. These fluctuations create a sort of background energy, sometimes called vacuum energy or zero-point energy. If this vacuum energy is real, and if it has the right properties, it could act like a cosmological constant, creating a repulsive force that drives cosmic acceleration. The problem is that when physicists try to calculate how much vacuum energy should exist based on quantum field theory, they get a number that's about 10 to the 120 times larger than the observed dark energy density. That's 1 followed by 120 zeros. It's the worst prediction in the history of physics, off by 120 orders of magnitude. Clearly, something is wrong with this calculation. Either our understanding of quantum fields is incomplete, or there's some mechanism that cancels out most of the vacuum energy, leaving only a tiny residual amount that we observe as dark energy. Nobody knows what that mechanism might be. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. An alternative explanation is that dark energy isn't constant but changes over time. Maybe it's a new type of field, sometimes called quintessence, that has different values at different times and places in the universe. This would explain why dark energy seems to have become important relatively recently in cosmic history. For the first 9 billion years after the Big Bang, matter and dark matter dominated. Expansion was slowing down. But then, about 4 to 5 billion years ago, dark energy started to dominate. Expansion started to accelerate. If dark energy is changing over time, then its future behavior is uncertain. Maybe it will continue to accelerate expansion forever, leading to a cold, empty universe where every galaxy outside our local group eventually disappears beyond the horizon. This scenario is called the Big Freeze or heat death. Maybe dark energy will weaken over time, allowing gravity to slow down expansion and possibly even reverse it, leading to a big crunch where the universe collapses back on itself. Maybe dark energy will strengthen dramatically, accelerating expansion so much that it tears apart galaxies, stars, planets, eventually even atoms in a big rip. We don't know which scenario is correct because we don't understand what dark energy is. All we can do is measure its current effects and build models that fit the observations. Current observations favor the simplest model where dark energy is constant and expansion accelerates forever. But observations can only tell us about the past and present, not the future. We're extrapolating, assuming that dark energy will continue behaving the way it does now. That assumption might be wrong. Another mystery is why dark energy has the value it does. The density of dark energy is incredibly small, about 6 times 10 to the negative 10 joules per cubic meter. That's roughly equivalent to the mass energy of 6 hydrogen atoms in every cubic meter of space. It sounds like nothing, and on small scales, it is nothing. In your room, in the solar system, even in the galaxy, dark energy is completely negligible. Its effects only become important on scales of hundreds of millions of light years. But why this particular value? Why not 0? Why not 1 billion times larger? If dark energy were much larger, it would have dominated much earlier in cosmic history. Expansion would have accelerated so fast that galaxies couldn't form. Matter would have been pulled apart before gravity could collect it into stars and planets. The universe would be empty, featureless, sterile. If dark energy was 0 or negative, expansion might have slowed or reversed. The universe might have collapsed in a big crunch billions of years ago. Or it might still be expanding, but so slowly that the cosmic event horizon would be much farther away, possibly infinitely far. The value we observe seems fine-tuned to allow structure formation, but also to ensure eventual isolation. It's large enough to matter on cosmic scales, but small enough that galaxies had time to form before acceleration became dominant. Some scientists argue this is evidence of a multiverse. Maybe there are many universes, each with different values of dark energy. Most of them are sterile, either expanding too fast for structure to form or collapsing too quickly. But a few, including ours, happen to have values that allow complexity, structure, life. We observe the value we do because we couldn't exist in a universe with a drastically different value. It's a selection effect, not a fundamental law. This is called the anthropic principle, and it's controversial. Some physicists find it satisfying, an explanation for why the universe seems fine-tuned for life. Others find it unsatisfying, a way of giving up on finding a deeper explanation. The debate continues, and it probably won't be resolved until we have a better theory of quantum gravity that can explain where dark energy comes from and why it has the value it does. For now, dark energy remains one of the biggest mysteries in cosmology. We know it's there. We know it's accelerating expansion. We know it's pushing distant galaxies beyond our reach. But we don't know what it is, why it exists, or whether it will continue forever. All of this uncertainty makes predictions about the far future somewhat speculative. We can say with confidence that distant galaxy clusters are receding and will eventually move beyond our cosmic event horizon. We can calculate when that will happen based on current expansion rates. But we can't be absolutely certain because we don't know if dark energy will remain constant. If it changes, all our predictions change too. The universe might surprise us. It has before. The discovery of cosmic acceleration in 1998 was a complete surprise. Nobody expected it. It overturned decades of assumptions about how the universe should evolve. Future observations might overturn current assumptions just as dramatically. Maybe dark energy will decay, weakening over time, allowing gravity to reassert itself. Maybe it will strengthen, accelerating expansion even faster. Maybe it will reveal itself to be something entirely different from what we currently imagine. The universe has a way of being stranger than our theories predict. And it raises questions about the nature of the universe itself. If inflation created vast regions beyond our horizon, those regions might have different properties, different laws of physics, different outcomes. The universe we observe might be just one small patch of a much larger, much stranger whole. For humanity, this means our future, if we have a long-term future, is one of exploration within limits. We can spread throughout the galaxy, potentially the local group, but beyond that, we face an impassable barrier. We can watch distant galaxy clusters recede into the distance, knowing we'll never reach them, never explore them, never know what they contain. It's a humbling thought, a reminder that the universe is vast and indifferent, and our ability to explore it is fundamentally limited. But it's also a call to appreciate what we have. Our local group contains thousands of galaxies, trillions of stars, more worlds than we could ever visit. It's a vast territory, rich with possibilities, and it's ours to explore. And within that territory, we might find other life, other intelligence, civilizations that arose independently in nearby galaxies. The odds aren't great, but they're not zero. If life exists in Andromeda or the Triangulum Galaxy or any of the dozens of dwarf galaxies in our local group, we could make contact. We could exchange signals, share knowledge, perhaps even meet in person given enough time and technology. That possibility, however slim, is worth pursuing. Because even if most of the universe is beyond our reach, our local corner isn't. And that might be enough. So as we look out at the night sky, at the stars and galaxies scattered across the darkness, we should remember what we're really seeing. We're seeing light that's traveled across expanding space, light from galaxies that are farther away now than they were when that light was emitted. We're seeing a universe in motion, growing, accelerating, pulling itself apart. And we're seeing the limits of what we can ever know, the boundaries of our cosmic neighborhood, the horizon beyond which we cannot pass. It's a strange and beautiful truth, one that changes how we see ourselves and our place in the cosmos. We're not at the center of the universe. We're not special in terms of location or significance. But we're here, we're aware, and we understand, at least partially, the forces that shape our reality. And that understanding, limited as it is, connects us to the universe in a profound way. We're made of atoms, forged in ancient stars, living on a planet, orbiting an ordinary star in an ordinary galaxy. Surrounded by a cosmos that's expanding faster than we can ever travel. We're isolated, temporary, small. But we're part of the story, a brief chapter in the long history of the universe. And maybe that's enough. The universe is expanding so fast that aliens will never reach us, and we'll never reach most of them. But here, in our local patch of space, we can look up, wonder, explore, and try to understand. We can ask questions, seek answers, and appreciate the strange and beautiful reality we inhabit. That's what makes us human, that curiosity, that drive to understand, even when the answers reveal limits we can never overcome. The universe has given us a bounded playground, vast but finite. And within those bounds, the possibilities are still endless. Thanks for joining me on this journey through cosmic expansion and its implications. If this changed how you think about the universe, about the possibility of alien contact, about the future of humanity among the stars, then the time was well spent. Keep looking up, keep asking questions, and remember that even in a universe expanding faster than we can travel, there's still so much to discover right here in our cosmic neighborhood. The aliens beyond our reach might never know we exist, and we might never know about them. But that doesn't make our existence any less meaningful, or our search for understanding any less important. We're here, we're aware, and that's something worth celebrating. The universe is expanding, but our capacity for wonder and understanding isn't shrinking. If anything, it's growing, expanding along with our knowledge, reaching toward horizons we can see but never cross. And maybe that's the real message of cosmic expansion. Not that we're limited, but that within our limits, we're free to explore, to question, to understand as much as we can. The universe doesn't make it easy, but it makes it possible. and that's all we can ask for.